No frogs today, I'm afraid. Well, the invitation to give this talk stated that it should be aimed at a general mathematical audience, and that means it could be somewhat technical. Now I see it advertised here as for a general scientific audience, which is not the same, a little technical if at all. And it seems to be part of today's conference on quantized flux, which I didn't quite appreciate, associated with the theme of the ongoing Newton Institute program that's just been mentioned on topological dynamics. I hadn't quite realized the talk is associated with that program. It isn't much. So I feel a bit like a point mass in one of those 19th century Cambridge tripos problems, attracted elastically by springs to the three vertices of a triangle, not equilateral, in this case seeking an equilibrium. But I interpret this indeterminacy as giving me the freedom to talk about anything I like. Okay. And this will be a circle of ideas that sprang from the fertile mind of my fellow quantum mechanic, Yakir Aharonov, and he is a physicist of great originality. My colleague Sandu Popescu, one of his former students, also a former fellow of this place, likes to say that Aharonov has spent his life avoiding mathematics. But in fact, his ideas are deeply mathematical, albeit implicitly so. And they impact on several areas, not just quantum. Now, I've developed some of those ideas which resonate actually with my own scientific preoccupations over the years, and I'll tell you about them, starting mathematically and gradually with digressions, eventually exposing their quantum core. Okay, so we don't really need those lights actually, if you can turn them off wherever. Thank you very much. Okay, well, this is about functions that oscillate faster than they should. Okay, if you imagine a band-limited function, that is a function whose Fourier content is limited, there it is, then conventionally you expect, and it usually is true, that the fastest variation corresponds to the largest Fourier components. Nevertheless, and it's counterintuitive when you first encounter it, such functions can oscillate arbitrarily faster than their fastest Fourier component over arbitrarily large intervals. They can superoscillate. And this suggests implications in several areas of physics, which I will get to. There are a number of recipes for superoscillatory functions, and I shall start with them, beginning with the 0th example, which is rudimentary and a demystifying example. Imagine you have the silly function cos x plus 1. Okay, well, there it is, and of course it has three Fourier components, 1 and minus 1 and plus 1, and it has these zeros, it goes down from 2. Now perturb it by subtracting epsilon squared. Well, now you produce a function with little close-lying pairs of zeros, there they are, separated by epsilon, and if you would see just this part of the function, you might be tempted to think it's part of some function with much larger Fourier components, because it looks as though it's fast oscillating if you just see that little bit where the function is very small, indeed small of order epsilon squared. So that idea, enormously elaborated and obsessed upon, is part of what I'm going to speak about. So my second example comes from physics. I want to consider, we've heard actually several talks today mentioning these, but not everybody was at those talks. Wave vortices, which are also called nodal lines, phase singularities, wave dislocations, in the old days we called them. And these are in classical or quantum waves in empty space, satisfying the Helmholtz equation with a wave number k0 in the plane for the moment. And the solutions are superpositions of plane waves, all of which have the same wavelength, the same modulus of the wave number, same wavelength 2 pi over k0, but different directions. So such superpositions. And if all these k vectors are real, then all sections of these waves are band limited. That's a spectrum. It's a ring spectrum. And we will be looking at some such functions. the length of the local wave vector, which is how fast the phase is varying, a measure of the rapidity of oscillations, can exceed, and does often exceed, k0. I will show you how that works in a concocted example, which is a high-order vortex. Well, to satisfy this equation, by the way, excuse me, this will have a physical meaning which we'll talk more about later, but at the moment it's parallel to the direction of energy flow, or the Poynting vector if it's optics. Okay. Now, here's a vortex of order m. Don't worry about this Bessel function. You need it to satisfy the wave equation. It has this angular momentum of strength m associated with it. The phase increases as you go round in phi. Well, here it is. Here's a map of the phase, color-coded. For 10, there are 10 reds. Red is crest, let's say, and green is troughs. And around the vortex core, the phase increases by 2 pi times this m. Now, what does that mean? It means that when you're very close, here's a wavelength, the phase can vary arbitrarily fast on scales much smaller than the wavelength. And the local wave vector, there it is, it's of order this m divided by the radius. Well, here is the local wave vector. It circulates around. That's why these things are called vortices. The energy swirls around. And it's band limited because if you write it, well, I told you before why it is from the wave equation, but these Bessel functions are just superpositions, continuous, of plane waves going in different directions. Okay, now let's look at this function as you fly by the vortex. Okay, just a function of one variable, x. Well, here it is. I've looked at, it varies enormously because the vortex is an nth order 0. So you go near to it, you smell it, and so you need to make a log plot. And to see the oscillations, just take the log of the real part. There it is. Now, here you see the wavelength, and when you're far away, it oscillates as it should on the scale of the wavelength. It's the real part, so twice as many zeros. These are the zeros, these spikes. But when you zoom in and look what happens near the vortex, then you see that what's oscillating is much faster than you would expect on the basis of its Fourier content. But notice this, e to the minus 30, these superoscillations are exponentially weak. That's how a function can oscillate, not contradicting the uncertainty principle or any of the known inequalities, because it does so where it's exponentially small. We'll see much more about that later, and that's the origin of the word weak, which will come in later. Okay, perturb it a little bit. I mean, it's a singular thing. You have to force vortices. They don't naturally want to coincide with each other. And if you perturb, here we're perturbing, let's say, with 1/10,000,000th of a bit of J0, which doesn't have a vortex, and the vortex splits. Here's a wavelength, okay? And the separation is about 20% of a wavelength. You can calculate it. And it splits into 10 ordinary vortices of strength 1, typical ones. We'll see we're making a progression towards typicality. Will be completely typical in a while. Okay, now, of course, here, it's not just the phase that's varying rapidly, it's also the intensity. And here is the intensity on the scale of the wavelength, giving the lie, by the way, to the old sort of folk belief that in these optical fields you don't see much structure on scales smaller than a wavelength, and we'll see more examples of that later. If you look at these geometric structures of the phase and of the intensity, they do exist. There's a lot of structure. Now, as I said, this is not paradoxical because in the superoscillatory region the wave is exponentially small in the number of superoscillations. Here's m, the number of them. Right. Now I have a second example, which is a mathematical one. Okay, and it's very, very simple. I looked at this with Sandu Popescu. Here it is. Look, take a function of x. It's just cos x over, there's a large integer n, plus I times a greater than 1 sine x over n, and raise it to the power n. Okay. What does that do? Well, let's look at it for small x. Well, you simply expand and raise up and take the log, do what we always do. And this is locally a single oscillation with a wave number a. Okay, a is greater than 1. However, if you expand this out sort of exactly, it's a Fourier series, and the Fourier series has Fourier coefficients, none of which is greater than 1. So here's a Fourier series, they're all less than 1. In fact, so all the Fourier coefficients are smaller than this oscillation near the origin. Okay, well, you have the coefficients there, and this represents superoscillations with a factor A greater than 1 faster than normal oscillations. Now you can also calculate the coefficients, and I don't want to discuss them in detail, but they reveal something, -1 to the m, so they nearly cancel each other out. So all these phenomena I'm going to be speaking about are phenomena that arise from almost destructive interference. Okay, well, here it is again. Let's look at the local wave number, the local phase gradient. You can plot it out. It's a periodic function, and as you go to half a period, it goes from 4, which is of course superoscillatory because you'd expect 1, down to normal oscillations, and then down to sub-oscillations. Now there's nothing surprising in a superposition of Fourier oscillations oscillating more slowly than the largest Fourier coefficient, because those slower oscillations are all there. That depends on how big they are. Okay, well, here's the function. Again, I'm plotting this logarithm real part. I've chosen 4. This is the oscillation you would expect on the basis of the Fourier content, but here you see you're oscillating 4 times faster. Okay. The number of superoscillations is proportional to this n. Okay. By the way, if you would look at the Fourier content, the power spectrum of this function, this superoscillatory wave is completely invisible, because locally, and I don't want to go into details, excuse me, not locally, for large n, it looks like a Gaussian, and here it is. You see k goes from -1 to 1. It's centered on 1 over a, no hint, and of course cuts off between outside -1 to 1. No hint that way outside here are these superoscillations. So you don't see it from the power spectrum. It is to do with interference. Okay, there we are. Now, so far I've presented this as a kind of curiosity, but it's interesting to ask, how common are these superoscillations? How natural are they? So let's again think about waves, and it's not much extra effort to think in d dimensions rather than just 2, it's just in 3 dimensions, for example. And here again, you've got a wave equation. Here you are, and we have complex scalar waves, which has several times have been discussed, represent physics of a variety of different sorts, classical or quantum, modulus and phase. The wave number, local wave number, is the gradient of phase. I mentioned it already, and that's the quantity we're going to be looking at. Now, superoscillations means that the local wave number is greater than the wave number of all the plane waves that you're adding together in superposition. And to understand typicality, naturalness, let's look at a random superposition, that is the sum of large numbers of these plane waves with random phases. Then you can do statistics. And if it's a large number, this is a complex Gaussian random function in d dimensions. Okay, and we want to know what's the probability that if you pick a point anywhere, it'll be superoscillating there. Okay, well, what is that? Well, first of all, you need to know the probability distribution of this quantity k itself, and then you integrate to find how much of it is superoscillatory, greater than the wave number in the wave equation. Let me show you what I'm talking about. Here is a random wave. I've color-coded the phase again, and here are the wave vectors. I haven't put the arrows on, and here are some vortices. Once again, this is one square wavelength, just to emphasize how rich structure you can get. So this could represent, for example, laser speckle, or waves, electron waves in a chaotic quantum dot. This isn't to talk about chaos. I can't resist telling you something I learned just the other day, which is the original definition of chaos in the first dictionary of the English language. This dictionary was Robert Caldry's Alphabetical Table of Hard English Words from 1613. It's almost 400 years ago. Chaos, a confused heap of mingle-mangle. Beautiful. Never mind. Anyway, here we are. And this is I say one square wavelength. Now, here I've shown bright, coloured, the regions where this is superoscillatory, and it's quite large. You can see that. I've cut out this here region where it isn't. It's oscillating slower than the largest Fourier component. Of course, this includes the vortices, where, as I've already told you, the oscillations are very fast indeed. So, quantitatively, what can we know? Well, it's a calculation, a nice calculation. I won't show you the calculation, Gaussian random function theory. And the result is that you can find the probability distribution as a function of dimension. What probability distribution of this local wave number? There it is. Different curves correspond to different dimensionalities, and we're interested in how much of it, this part here, is superoscillating, the bit that's greater than k0. An easy calculation. Here's the answer. Now, it doesn't actually vary that much as you go from one dimension to infinite dimensions. It varies from about 0.3 to about 0.4. There's only one value for which it's rational, and that's 2 dimensions, and that was a calculation that Mark Dennis did, which is the pioneering calculation of a great number of them, some of which I'll tell you as we proceed, of these probabilities of getting this peculiar behavior in different situations. Okay. Now, given this behavior, one naturally wonders about optical fields which can vary, propagate, and show you objects which are smaller than the wavelength. And this is different from superoscillation. It's super resolution, and it's worth just spending a moment deconstructing these different concepts. You see, you could combine in an optical image with some given wave number using light of a given wavelength, combine superoscillation with super resolution. Normally, people think of doing that by having evanescent waves, which decay exponentially with distance. But let's look at these concepts. You see, there are 3 lengths involved. There's the scale of the feature one's thinking of, there's the wavelength of light, and there's the largest Fourier component transverse in one's image. Now, superoscillation means that the feature you're looking at is smaller than the scale corresponding to the largest Fourier component. I've explained this already. Superresolution means that it's smaller than the wavelength, and no evanescent waves, only propagating waves, means that the scale, that the wavelength is smaller than the scale of the corresponding to the largest Fourier component. For example, in a paraxial field where all the waves are travelling almost in the forward direction, the sideways scale is much larger than the wavelength. So these are 3 concepts to be disentangled, and people begin to use these ideas in making schemes for optical super resolution. But there are 2 cautions that I want to bring to your attention. One is that because they're delicate interference effects, they're very sensitive to noise. I want to just give you an example. Suppose you have your function, which is this Fourier superoscillatory thing, but you put some random phases on, epsilon's worth of random phases. Okay, well, let's take an example from this function with Popescu. Here's where you have no noise, and here are the superoscillations, and here are the oscillations you would expect on the basis of the Fourier content. So it superoscillates here. If you add 1/100,000th of randomness, then you preserve the superoscillations. But if you go to 1/10,000th, then you've lost it. And of course, 1,000th, you've lost it completely. So it's very sensitive to noise, to be borne in mind. But you always have to pay for anything improvement of this kind. Okay. Now, secondly, you have to be very careful to avoid these superoscillations being blurred out by propagation. And I want to talk about a fine structure in an object, superoscillatory fine structure, so smaller than the wavelength, okay, structure, and the Torbert effect. Now, the Torbert effect, the same Torbert who invented the photographic negative and the photography that we used until recently, near Bristol, was also a physicist, and he discovered that experimentally that if you have a periodic object, then at certain distances, due to interference, the structure repeats, repeats, and repeats. So it reforms itself by interference. Okay, now that's an effect of paraxial optics, and we want to understand whether it's destroyed by the fact that inevitably there are angles which are not small, or rather whose smallness is not small enough. So here we have something that's periodic in X and periodic in Z. This is a paraxial wave. These are the Fourier coefficients of the object in the plane Z equals 0. Okay. It's periodic in X, yes, with period 2 pi times d, and periodic in Z as well. That's the Torbit effect, it's periodic in Z. Okay, but now you realize that because of non-paraxial, I mean, what is paraxial optics? It approximates cos theta by 1 minus a half theta squared. That's the n squared in there. But of course it isn't exactly that. As it's a square root, you're approximating a circle by parabola, and so you've got corrections, the first of which is fourth order. What does that do? It means that the image you'll get on propagation is going to be smoothed in some way. What is the smoothing? Well, the smoothing is some integral. It's an interesting integral. I won't discuss the details. What we want to know is, what's the width of it? Well, the width of it is, if you have a wavelength lambda, the width of the smoothing is, well, it's the cube of lambda times the distance you've travelled to the power 1/4. That's a length. That tells you how much these effects that you normally ignore, when you see the Torbit effect, how effective that smoothing is. It's normally small. There it is. However, if you want an object of period d, you see this reconstruction at this distance d squared over lambda. When you put that in here, you get square root of size of your period times lambda, which is much greater than the wavelength, so you've smoothed away all sub-wavelength superoscillations, which is a negative conclusion. It's not fatal, but it's a negative conclusion, and it's why the naive implementation of this scheme doesn't work. But I'll tell you a far-field effect which does work, but which is actually very old. This goes back to the 1940s in radar practice, theory and practice, a realization by Shelkunov, which was imported into optics but largely ignored until recently by Toraldo de Francia in the 1950s, which is this. You have an aerial. Let's just look at this particular kind. I mean, an antenna, which consists of n+1 sources arrayed over a distance L, and you're looking at, it's an end fire array, you're looking at what happens, what the radiation pattern is as a function of angle. Now, normally you would think, and it's normally true, that if you want a tight radiation pattern, you have to arrange your sources to be over a length much greater than the wavelength. However, we're interested in, let's say, the cones of silence. The cones of silence are the angles for which this is 0. The radiation pattern has its side lobes separated by these cones. Now, you can, however, and this was realized in the old days, and you get a new insight into it using these modern ideas that come from Aharonov, that you can choose the amplitudes and phases of the sources to make the radiation pattern arbitrarily narrow, even if the length of the array is much smaller than the wavelength. This is now in the far field. So this is, it was called super gain or super directivity, narrower than Rayleigh, is the transposition of faster than Fourier. Okay, well, how does that work? Well, here is the radiation band. It's just a sum of sources with the appropriate phase factor to correspond to waves reaching the far field. And I've put some phases in here which are designed so that if all of these phases are 0, this is coherent in the forward direction. Okay. Well, traditional optics or radio is where all of these are 1. If they're all 1, then you have to have a very large antenna to get a narrow pattern. Here's 10 wavelengths, 3 wavelengths, 1 wavelength, quarter of a wavelength. So you don't get a narrow pattern until you have a large array. However, to create supergain, notice this. If you have this variable, which appears in the phase, then the function, the radiation pattern, is a band-limited function of x, and its largest Fourier components are e to the plus or minus I x, just Fourier coefficients 1 and -1. So I've chosen this variable, and here's the Fourier series. So you might try playing in such a way that you make this a superoscillatory function, but it's not quite good enough because it isn't just oscillations you want some narrow chosen function. So suppose you want a function whose Fourier transform is g of a. Okay, so in other words, what you hope is that your radiation pattern will be at least approximately the Fourier transform that's the function that you desire. Well, here's what you do. You choose any superoscillatory function, like the one I showed earlier with Popescu, with the property that, near the origin, it does have this exponential property. Then, if you use this superoscillatory function and you multiply it by g and then take the integral, then what you'll find, of course, is that since near the origin this behaves as you want it to, then approximately at least you'll be able to reproduce your desired radiation pattern. So what does that mean? Well, let's look at a sink pattern, very smooth, with some arbitrarily small width. You want to make that. Okay, well, you do the calculation, and then you find that for large n, indeed, this has a sink pattern with a width smaller than you would expect from the Fourier content by this w that you can choose arbitrarily. Well, here you see it. I have an array which is a quarter of a wavelength long, but lots and lots of elements, 200, 400, 500, with these carefully chosen phases, so they almost cancel. And look, as you go between 400 and 600, you do indeed see this narrow pattern. As you increase it further, it remains the same. So this does work, and it's different from the way in which it's explained by the radar people, but of course it's equivalent. But with superoscillatory functions, you can easily create large numbers of these radiation patterns to order. Of course you pay a price. What is the price? The price is that here's the natural variable, and you need to sample the superoscillatory range, because it's only between plus or minus KL. So this has got to lie within the range where the function is superoscillatory. And we saw that it increased enormously outside. So what happens if you don't do that carefully? Well, these enormous values outside the interval correspond to imaginary angles, which is equivalent to saying it's beyond backwards, if you like. This corresponds to the near field. It means that the individual elements of the antenna, the sources, have to be enormously strong. And this is a well-known fact. It's why these are not used all the time. They're inefficient, and in fact what happens is a lot of energy is lost due to heating. Still, let's have a look. I say the individual A's are enormous to produce this modest superoscillation, and it results, as I said, from near-destructive interference. So look, here is the case I showed you before. 100, n is 100, 1/40th of superoscillation. Look, somewhere in here is your little sink function. You must be careful not to sample 10 to the 158 outside there. But still, if you do zoom in, then you see your sink function. So it's terribly weak. Of course, in practice, you would never want or be able even to dream of such a degree of superoscillation, but a modest one could be achievable. Now, imagine that you're doing signal processing, and you have a perfect low-pass filter, and from which a function comes. Now, function f of t, function of time now. Now, suppose this function is superoscillatory, and you just look at a bit of it coming out of the filter. I think pretty well every engineer would come to the conclusion that their filter is actually leaky, but it need not be. It could be that you're just seeing a bit of a superoscillatory function. Now, you can pursue this idea along the lines that I just explained for the antenna, but you could do this, for example. You could reproduce the whole of Beethoven's Ninth Symphony, lasts for an hour, and you want nice hi-fi, so you 20 kilohertz for good reproduction. You can do it with a 1 hertz bandwidth signal. And in an old paper I have an explicit form. Beethoven is this and the superoscillatory function is that. Well, you pay a price outside the hour, and this would correspond to the sources you would need to produce this. It rises to e to the 10 to the 19, so don't even think of trying it. But still, in principle, you can do it. It's this miracle of near-destructive interference produces these fine, tiny little tails. Now, in quantum physics, now we're getting to the heart of Aharon's original idea, the large K superoscillations in those waves I started by telling you about represent something called weak values, I'll explain it, of momenta. And in general, these are values outside the spectrum of the operator you are measuring. That sounds paradoxical. It's that in quantum physics, all measurements you think must be somewhere within the spectrum of the operator you're measuring. Not so in this case, which I'll explain. Now, I first heard of this when Aharon visited me more than 20 years ago, and he loves paradoxes. He's written a book, Quantum Paradoxes, and he said to me, you know, you can have a box. I envisage a box, and in the box there's red light only, but I open a hole in the side of the box, and out would come a gamma ray. I thought, what is this nonsense? You know, and of course, gradually I came to realize that what he was envisaging was what I've been telling you. You would have the wave function in there with this finite red light spectrum, limited, but you can superoscillate a bit. If you catch that bit, you'd think that what comes out is actually of higher energy than you would have imagined. Now, let me start to tell you about these ideas. Okay. In general, the weak value of some observable corresponds to a quantum state that you start with, and normally that's all you have in the usual measurement scheme in quantum mechanics, but you don't just measure it in that state, you select afterwards, he calls this post-selection, a different state, phi, and create this object whose general significance I will tell you in a little while. Well, you take the matrix element and you divide by the overlap. That's generally a complex number. The imaginary part has an interesting meaning, but I'm not going to speak about it, so take the real part. Okay. Now, let me explain that in two stages why this is actually sensible in some cases that you might want to think about. So imagine that you're looking at something state that depends on position, and you're looking at a particular position and you want to define the local expectation value of an operator. Well, independently of all of this, a natural way to do it is to say that you measure this operator, A, but you multiply it by the position operator restricted to the place you're looking at. You have to symmetrize it, of course. You do all that and you go through. Now, that's a natural definition. But when you work it out, actually, you calculate it, it's precisely the weak value of the operator you're measuring where you're post-selecting position. That makes sense, okay? That's a special case where you're post-selecting position. Now suppose that the operator you're measuring is local wave number or wave vector, the momentum operator, minus I grad. Well, then you work out the weak value, according to this scheme, of the momentum operator at a particular place, and you go through it. It's precisely this, what we've called the local wave vector. So it all fits together nicely. Okay. And just to rub the point in, if you have some superoscillations, this K lies outside the spectrum of the operator. Well, it's the wave number operator. What's the spectrum of it? It's the expectation value of a delta function. It's precisely the power spectrum as usually conceived. Very good. Well, a question you could ask, and Pragya Shukla and I did ask it, is, you know, how common is this phenomenon whereby this weak value of something can be outside the spectrum? We call it super weak. Of course, a special case is superoscillation. Here you are again. It's this quantity A, and we want the probability distribution of A averaged over all possible pre- and post-selected states that you might choose in a Hilbert space, and there's a natural measure for that, which I won't tell you about. And we looked at the case where there are a large number of eigenvalues. Then the fine scale distribution doesn't actually matter. And then you do a calculation. It's a calculation that I won't tell you about. But again, the super weak probability is the integral of this outside the range of the operator. Well, you do a calculation, and in fact the answer depends on exactly how on a coarse measure of the distribution of the eigenvalues here. It's largest when they're concentrated near the ends of the interval, and it's 1 minus 1 over root 2. Very good. So that's a nice general universal result. There's this one parameter that appears here, and here's the distribution. You're looking at the tails. Of course, this doesn't work if you just have 2 states, because this is for large n. Well, that's a different calculation. Mark Dennis, Ben McRoberts, Pragya Shukla, and I wrote about that. Then the distribution is a little bit different. It's this one. There it is. You'll think, for example, a spin half. That has 2 states. Now you're measuring the spin half with all possible combinations of pre and post-selected states in this scheme where you're see how you can get these very large values comes from that denominator. If the 2 states are nearly orthogonal, then which means that you're measuring quite rare events, but still this quantity that you're measuring is in the tail. That's how it works. Okay, well. Then the superweak probability is almost the same. It's 1/3. We keep getting similar numbers, slightly different ensembles in different cases. Now, this explains, or rather doesn't explain, it gives extra insight into the very first calculation that Haronov and his colleagues did in 1988, again expressed in a paradoxical way, on these weak values, how the result of a measurement of the component of a spin half particle could turn out to be 100. L equals 100, you'd expect between -1 and +1. Well, now you can calculate how likely that is, because we know the probability is super. If you just randomly choose the pre and post selected states, what's the chance that you'll get a value L greater than equal to or greater than 100? And well, the answer is it's 1 part in 120,000. It's an exact calculation. Okay. Now then, let's go back to what I promised you, which is the origin of these weak values. When you measure something in the traditional scheme in quantum physics, you're looking at a pointer and it shifts according to the value of the thing you're measuring. So you have to couple what your system is to some pointer. Okay, and let's discuss that. Okay, you measure some operator, this operator, by briefly coupling to a pointer with a coordinate x. And maybe I've called it q, I can't remember. I think I've called it q later, forgive me. And the initial wave function of the pointer, some localized thing, it's a quantum thing, this pointer, phi of q. Okay. Now the final wave function, it's the, this is the von Neumann way of describing a measurement. You couple your operator to the momentum corresponding to your pointer, and then this exponential is the shift operator. So very natural thing, you'll shift your pointer. But you're pre-selecting with state I and post-selecting with F. Here they are. Forgive the change of notations. Okay, so the wave function of the pointer, there it is. You can do a calculation, and it's a quite natural thing. It's a sum of superposition of copies of your pointer, each one of them which is shifted according to one of the eigenvalues of the thing you're measuring. And that's normal, what you'd expect. You've got a superposition, then your pointer is blurred out, but it basically corresponds to lots of separate shifts corresponding to the individual eigenstates that you're measuring. Okay, so there it is once again, superposition of copies. Okay, but now suppose that your initial wave function is very broad, much broader than the spectrum that you're looking at. That seems like a bad measurement, of course, because you want it to be refined, but suppose, and that means all the copies overlap and interfere. And then, if provided the Fourier transform of your pointer decays fast enough, for Gaussian it does, it's an interesting question that we've looked at, what happens when it's not, but never mind. Then, by a mathematical miracle, the pointer wave function is almost cancelled by destructive interference, but it's resurrected far outside the spectrum, super shifted by this super weak value, which is the reason for studying it in the first place. So then you find, and I won't give the calculation, I can't spell destructive, there it is. Now this is the pointer shifted by the weak value. It's a calculation, and Yakir Haronov and his colleagues had this result, and they used a heuristic argument to get it, and their insight was very good, it's correct, but it's more interesting to deconstruct it and understand rigorously where it comes from, and I'll show you that now. Again, this is work with the Pragya-Shukla. We looked at different analytic forms of pointers, but I won't discuss that. So imagine that your pointer has a width delta, and we're going to increase delta and see what happens. I don't want to go through the details of this, except to say that I'm looking for a case where, here are my different graphs, which I'll go through in a moment. I'm looking for a case where the range of the spectrum goes from -10 to 10. That's where you expect the pointer to end up being, some blurred out version of that. But I'm choosing a case where the supershift is 30, so we'd be outside, it's here. Well, look, here, if you have not a very broad wave function, there it is, you're nowhere near the supershift, you're lying comfortably within the spectrum. Now, as you increase the delta, it starts to move out, and eventually it moves outside the spectral range, and by the time you get to 10, it's a Gaussian, broad, as I've said, but completely outside. So that's this scenario and how it works. Just to remark that, look, 10 to the -11, that's why these are called weak measurements. You're looking at very improbable events. You're post-selecting unlikely things, so you can get extreme values. All of this, I've tried to explain to Yakir, is a sort of unusual branch of what a statistician or probabilist would call large deviation theory, but it's unfamiliar because you don't normally include interference in that in those schemes. So now let's go back to this wavy thing I talked about before. We've got these wave vector lines. I didn't put the arrows in. And what do they mean? Well, what it means, you now understand what it means. It means that these large momenta correspond to momentum that will be transferred in individual photon impacts on a small detector. So you put an atom there in a trap, for example, and you would see that the atom would get kicks larger than the momenta in any of the plane waves that make up the superposition. That sounds paradoxical, and this whole subject is surprising in that sense. But what does it mean? I mean, how can one understand this? Well, it's this. If you contrast the wave vector with the current or pointing vector is the imaginary part of psi star grad psi, which actually is the wave vector, but multiplied by the intensity, which of course is very small near a vortex. Okay, so it's weighted very small. Now, that's what you'd see on the average. Now, we're not thinking about the average, we're thinking about these individual impacts, which are very rare. So what this is doing, it's deconstructing this average into its individual quantum events. And what is this average? Well, it's actually just radiation pressure. So what this does is it shows near a vortex, or in any region where you've got superoscillations, you would expect that radiation pressure is very weak because it's everything is small there, but still it exists. But this weak radiation pressure, when deconstructed individual impact, is made of very rare events which are actually extremely strong. And I would like people somebody to do an experiment of this kind. I have various ideas for more precisely how one might go about it, but so far nobody has. It will be an interesting quantum effect to see something being kicked with a momentum that isn't present in any of the waves that make up the field. Well, one can play nice games. I'll show you just a few of them now, once one has this idea. One is retropropagation. Okay, 2 dimensions, let's say. You can have all plane waves moving forwards, but still the local wave vector in the z direction could be negative. There could be local regions where the energy is flowing backwards. And how does that work? Non-paraxial now, nice wave, here it is, x and z, sum over waves, all of which are band limited, okay, so no excessive Fourier components. Here's a picture. I'm not going to go through the details of this, but 21 waves, they're propagating in the z direction. The angles are uniformly distributed between 0 and pi, no backward waves at all. All the waves are going forward, but in these regions, which of course include the vortices, by the way, which are here you've got these lines are wave crests and troughs, they're phase curves, but these shaded regions are the regions where the energy is flowing backwards, okay, and there's probability, I mean, very improbable. I mean, in this particular case, only 5% of the space is backward going, so I don't want to discuss this anymore. Another scenario is you can talk about relativistic waves, and you can have waves consisting of superpositions where all the group velocities are less than the speed of light, subluminal waves, but still the local group velocity can be superluminal. Okay, well here's the Klein-Gordon equation, and it has a dispersion relation, never mind the details, but there's a group velocity operator which you can easily confirm, and you have a superposition of subluminal group velocities. This is a general solution, and these A's are coefficients with phases that you can choose, and you can ask about the weak value, which is the local group velocity, and you can calculate it, and for some places in space-time, some events, this can be greater than c, greater than 1 in this normalization. So super weak here corresponds to superluminal. And here's a scan of one of these waves. These are the superluminal regions, group velocity greater than -1 or +1. In space-time, here are the regions of superluminality. And again, there are formulas which I don't want to bore you with. Always less than a half, but could be a half in some cases. Now, Dirac waves, electrons, a little bit more complicated there because the waves are now spinors. But still, you have the group velocity operator, which only has eigenvalues +1 and -1, a little bit like spin half. But still, you can have a pre-selection. You can pre-select your wave function is a solution of the Dirac equation. I won't go into why it is, but it is a general solution in one dimension, each with different coefficient, all less than 1. Now, you post-select with any spinor you like, and we're going to average over those spinors and also average over the coefficients here. And the weak value, no, you don't need to average. For a given choice of spinor you post-select, you have a local weak value, okay? And then you can average over, as I said, everything. And the result is always between about 0.3 and about a third, so quite a narrow probability distribution of superluminality. And I'll show you, I don't remember what spinor I chose to post-select with, a particular one, at a particular set of coefficients. And here again you see superluminal velocity negative, superluminal velocity positive. And now the regions in space-time have a different shape from Klein-Gordon. There must be reasons for this. There are interesting questions about the topology of these regions in space-time for which you get superluminal behavior, and you can get very rich and very varied structures by choosing different probability distributions of subluminal group velocities that you superpose. Now, to finish, I want to tell you a story about a year ago. You will remember, I'm sure, the exciting news from CERN that neutrinos had been detected traveling faster than light. Now, I, along with pretty well every physicist, thought this must be an artifact, a mistake, and indeed it turned out to be. However, before it was known to be a mistake, it was worthwhile trying to understand whether it was possible for this to be some physical effect which wouldn't cause the whole of physics to come tumbling down. Of course, it would be more interesting if it did come tumbling down, as we pretend to say. But it was worth looking whether this could be. And I had no thoughts on the matter. And Pragya Shukla called me from India and said, could this possibly be an artifact of a weak measurement? Okay, so I talked to my colleagues, Sandro Popesco and Nicolas Brunner, and we decided that it was conceivable that it could be one of these apparent superluminal effects, which there are a number of them in physics where you can't send any signals faster than light, but they're bits of wave packets which appear to catch up with other bits and move faster than light. And Nicolas Brunner had done actually an experiment of this kind in an optical analog. I mean, he wasn't thinking of neutrinos some years before, and so we wrote a paper, and I think that this was the first actual published paper on the matter. We summarized our conclusions in an abstract. Here it is in its entirety. And to our surprise, this achieved instant celebrity. It was picked up by Der Spiegel online, and we got all kinds of messages from all over the world about this silly abstract. So I think with some of the present audience, I hardly dare to use the word impact, but that's what we had. Well, so what did we do? You can't know until you do a calculation whether this would be feasible or not. And it's based on an analogy between neutrinos and polarization. Now, we had a nice lecture on neutrinos just a little while ago, but let me summarize the point. It's as though space is birefringent. And neutrino flavors, mu, Tor, and there is another one, but not very relevant to that story, so we were told, are not the mass eigenstates which propagate without change, but superpositions of them. Okay, it's a bit like it's precisely like if you just consider two flavors having a birefringent medium and then propagating states which are not the two polarizations that propagate without change, but some other state, and then that state will gradually change and oscillate between the two as it propagates. And these, of course, are the famous neutrino oscillations. Okay, so the initial state is some spinner here. It was mu neutrinos that came out of CERN and went down into Italy with some initial wave packet envelope and traveling with some momentum. So this is the initial neutrino packet, if you like. And the evolution with different energies for the two states in a superposition, plus and minus, and they're two group velocities, presumably subluminal, and if we just take the conventional view, distorts the wave that arrives at the detector. And you want to look at the final average displacement of the average position of the wave. Now, here's the point. If you post-select actually the same state mu that you start with, and remember that it's rotated a bit out of mu, it was conceivable this could generate a mean position corresponding to superluminal arrival. And that's what Nicolas Brunner and his colleagues had seen 10 years before in an optical fiber, in a birefringent optical fiber using polarized light. So we had to do a calculation. Okay, well, it turns out, I won't go through it, but it turns out that the effective velocity shift is the weak value of the velocity difference operator. That's what it is, and you can barehandedly do the calculation without thinking about weak values, but this is what it is. And this difference of group velocities is a property of the two neutrino mass eigenstates. So that, by the way, the group velocities then are the mean plus or minus this delta or half of it, and these are both subluminal. Okay. Now, it turns out when you do the calculation, the effective velocity shift is something. It's an amplified version of this difference of group velocities, amplified by some factor, which we were investigating. Could it possibly bring the superposition faster than c? Well, here's an exaggerated illustration of what might have happened. You see, here are I've plotted the strengths of them, not the phases. Here are the two Gaussians, two separate Gaussians, which are propagated with different speeds, almost in antiphase. So when you look at the superposition of them, there it is. It's weak, of course, and the supershifted position is outside the center of mass of the two separate Gaussians, and the idea was that perhaps this could make things greater than light, faster than light. But when you see, we don't know what the velocities of the neutrinos are, but from the mass squared, difference of mass squared, you know what the difference is, and so the most optimistic assumption for this scenario is that one of them actually is c, massless, and the other one is just a little bit less. But anyway, the separation of the group is actually 10 to the minus 24 c. But what the CERN people claim to have measured is something vastly bigger, 10 to the minus 5 c. So any operation of this scheme would have to give an amplification of 10 to the 19. Now, no way that can happen. It rules it out straight away. But just to really rule it out, this little factor here, which has to be nearly 1 for this to be a small denominator to cancel this, is only about 3%. So no way at all, hence our abstract. Okay. So, anyway, over the years, I colleagues have written a number of papers on these these ideas that came from Aharonov, but resonate with these vortex ideas that we've been developing since the 70s, actually. And they're all on my homepage. I won't go into that. So I think it's a rich circle of ideas, many ramifications, and much left to understand. Stop.
Are there any questions?
Yes.
In field theories, if you have superluminal behavior, usually it corresponds to Hamiltonian with negative eigenvalue.
Yeah.
Instabilities. Do you have something similar here?
Well, this is the Dirac equation. So, but all the eigenvalues superimposed here, they all have positive. Each of the individual plane waves, it's a different effect. Each of the individual Dirac plane wave solutions, they'll have positive group velocities. And I think they'll have positive energies as well. But the superposition doesn't. It's an example of, I gave several others of similar behaviors. So I think the answer is, it's not like that. You know.
At the back.
Did you try to fit this neutrino velocity data to the 1987 supernova?
No, because
There is a quite good data there.
yeah, yes, I didn't actually, and I don't know the status of that. Thank you for reminding me of this. No, we didn't, because we were just concerned with that particular experiment. But yeah, should be done. Yes, I know that you're talking about some neutrinos that seem to arrive too soon, right?
No, they arrived a little after.
Oh, they arrived a little after. Okay, well that.
They had a very nice
yeah.
you put a very nice profile of
Yeah,
them.
so they arrived a little after. Okay, but anyway, I mean, this 10 to the minus 24 is something that one would have to work very hard to achieve that. Yeah. Yes.
Did Aharonov tell you the probability of getting that gamma ray out of the box?
No, of course not. I mean, that was just it was. I mean, he didn't work out any probabilities. I mean, that's what we've done subsequently, developing the ideas. No, of course, no. Well, no, and it would. Of course, it would depend on having a very delicate superposition of nearby red light plane waves. No, he didn't. Of course not. No, but it was just. He likes provocation, and it worked. Sorry.
But related to that,
Yes.
If you extend your ideas to field theory,
Yes.
make a box out of which you get very high energy particles instead of making a huge accelerator.
Oh yeah, but of course, I mean that's the scheme, and I mentioned a version of it where I would imagine having an optical field in a cavity, and then in which you would hold a small particle in a trap. This was not field theory. I mean, you don't need field theory for this, but you would have a Maxwell field, a radio frequency field, as people do have in a cavity, but you choose it so that it has a phase singularity. That's not hard to do. I mean, several people have explained. Mark explained, for example, how to do that. And then you have a particle which will occasionally be hit by photons, and my prediction is that it'll be hit with energies which can be much greater than you might expect. Now, of course, it's not a source of energy, of course not, because it's an extremely rare phenomenon. We're looking at tiny tails of things, but still, it's a strange effect. So I don't know if that's what you...
It can work as an accelerator.
It's a what?
Instead of a huge acceleration machine,
Oh,
you have a small box.
yes. Yeah, well, so this is for the next CERN, you mean, which the world can't afford. Well, how shall I say? You've seen there's very small probabilities of getting these large effects, so don't hold your breath. Although, the cleverness of engineers is such that, given an idea, they can often implement things that we would have thought it's not impossible, just improbable, but very much so. Yeah.
There's another one just there.
Yeah, I just wonder to what extent these high local wave numbers are related with singularity of angle phase decomposition, because obviously,
Well,
where you have vortex, the original psi may not have anything no high derivatives.
Yes. Well, I mean, this old question of how you have whether you can have an angle operator, it's related, a phase operator, it's related. This old question doesn't play any part in these calculations. Now, it may well be implicated. I mean, I'll tell you something. I mean, it took surprisingly long before I realized that, in fact, these rapid phase variations close to a vortex of phase singularity are an example of superoscillations. And it came because experimentalists actually, very good, again, Mark mentioned it, Miles Paget, said, look, how can it be that the wave goes to zero near a phase singularity, near a vortex? Because doesn't that violate the rule that nothing can vary on scales smaller than a wavelength? And then we've been talking since the 1970s about fine structure in optical fields which have phase singularity, that I showed some examples, but I hadn't made the connection until suddenly I realized that there's an example it can do so without violating any theory because the wave is very small there. Now, in fact, this gives me an opportunity to say something else. Is the wave really zero there? The answer is not if you include quantum optics. If you go from classical optics to quantum optics, there's a quantum core. Mark Dennis and I have written about it, and other people have now developed the idea a little bit. It's a quantum core within which spontaneous emission dominates stimulated emission. I don't want to go into it because it's a longish story, and the core is much smaller than the wavelength. So, in fact, you could say that if you really would measure using a microscopic detector, you wouldn't find the exact zero there. Any more, it's because of quantum optics, because of the vacuum, basically. Any more than with sound, as I'm speaking now, this room is filled with a forest of phase singular lines of the acoustic field moving across your ears too fast for you not to hear them. Okay. However, you ask, is it zero? Is the disturbance zero? Well, no, because of course air is not a continuum. It has molecules, and if you go to a small enough detector, you'll hear the Brownian motion, even if you've got no signal. So once again, there's an acoustic core. The physics is different, but the general phenomenon is the same. So very fine scales. You have an acoustic core, and we've worked out how big that is. Some people claim to have detected the sound within an acoustic phase singularity. You have to be very careful. I'm not convinced that they haven't detected electronic noise in their amplifiers, so it's a subtle matter, actually. But I'm not answering your question, forgive me. So whether this has connection with this old problem of defining a phase operator because you don't have the right combination, whatever, there may be a connection. It would be interesting to explore it. We didn't actually. I mean, these calculations don't depend on that.
For example, if you just take scalar field.
Yes, that's for example, yeah.
Would everything be as singular as with complex field?
The complex field is a
I mean,
you mean real fields?
Just real.
I mean, just take the real part of, as I graphed indeed, of any of these superoscillatory functions, and they still oscillate faster. I mean, it's the same. It's essentially the same behaviour. It's just that for a complex field, gradient of phase is a nice quantity to calculate, but you still get the fast oscillation if you take the real part.
Well, as in the cinema, the lights seem to have come up, so we should